you need to know the difference between electron configuration, which is when we write out 1s2, 2s2, 2p6. That's called electron configuration. But orbital notation is when we start to draw our electrons using these arrows. Okay, we start to draw them out. So it gives us more of a picture. So when we represent orbitals, orbitals are just indicated by a line, right? A line is what we call an orbital. Some places will even draw it as a box is considered an orbital. An orbital that has one electron has one arrow in it, and if it has two electrons, it's got two arrows in it. Okay, and I'll expand on that here in just a minute. Yeah, an unoccupied orbital is represented by just an empty line. So if the line is empty, that means there's no electrons in that orbital. Yes? Right, so each orbital we know has a max of 2 electrons it can hold. And then we know in the d orbitals there are 5 different versions of those. So you would have 5 lines to help you represent the d orbital. Okay, I'll talk about that as we walk through. We have to follow something called Hund's Rule. And Hund's Rule tells us how do we put these electrons in our orbitals. Right. What order do we have to follow? All right, Hund's Rule says orbitals of equal energy are occupied by 1 electron before any orbital is occupied by a second electron. So we're going to talk about what that means, but I want you to write down that step of Hund's Rule, that portion of Hund's Rule. Orbitals of equal energy. Okay, all electrons in singly occupied orbitals must have the same spin state. So what that means is when we're drawing our electrons, you notice that in an orbital with 2 electrons had one pointing upward and one pointing downward. This is how I draw electrons, and really how electrons are supposed to be drawn, but I didn't have the power in PowerPoint to draw a half-headed arrow, so I had to draw a regular one. But this is really how you draw electrons, is with like a half arrow. Yeah. Okay, and when you draw them, you should always draw the positive one first, the negative one second. Okay, but I'll show you kind of what this means here in just a second. All electrons in singly occupied orbitals must mean they have the same spin state. Okay, so we're going to do an example with nitrogen. So I want you to find nitrogen on your periodic table. Nitrogen's electron configuration, I'll give the whole electron configuration, is 1s2, 2s2, 2p3. Agreed? That's the electron configuration. Okay? Now the orbital notation is when we draw it out. Oops, I can't spell. Orbital. So here we go. We're going to draw all of our orbitals individually. The 1s orbital, the 2s orbital, and the 2p orbitals. Okay, why did I have to draw 3 lines for my 2p orbitals? Each orbital can only hold 2 electrons, and we know there are 3 versions of the p orbitals. Right? I've drawn it out several times. The p orbitals, there's one version that goes there, one version that goes there, one version that goes there. 1, 2, 3 versions of the p orbitals can hold a total of 6 electrons. Oops. Okay. So we've drawn our orbitals, but now we have to start putting in electrons. And so we follow Hund's rule to tell us how we put electrons in. Okay? The first energy level is 1s. And Hund's rule says orbitals of equal energy are occupied by one electron before we occupy it by a second. But here, there's only 2 electrons that even fit into that orbital. Okay? There's only 2 electrons that even fit in that orbital. So we just put them in. They have to have opposite spins within that orbital. One pointing up, one pointing down. That tells us which direction the electron is spinning, in the positive direction or in the negative direction. Okay, so that energy level is full. The second energy level is the 2s orbitals. We need 2 electrons there. Okay, our next energy level is 2p, and it says we have 3 electrons in the 2p orbitals. Can we fill them like this? 1, 2, 3?
No. Yeah. That's how you're supposed to, right?
No. What's it say?
You have to make sure they all have 1.
They each need to be occupied by 1 before we occupy any orbital with a second. So we go 1, 2, 3.
Wait, is that not what you said? You said
Orbitals of equal energy are each occupied by 1 electron before we add a second. Nope. So look at what I'm doing. Don't disagree. Here's 1, 2, 3. Those are all singly occupied orbitals. We can't put a second one in.
until you filled out all of them.
Right, until we fill out all of them.
Yeah.
But I only need 3 electrons, so I'm not going to go back and put a second one there.
Okay.
I only need 3 electrons in the p orbitals.
But with that, you just said 2p3, right?
2p3, right? So I can't all electrons in singly occupied orbitals must have the same spin state. So when we're putting them in first, we always put in the positive one first. And so here, we put in the positive one, and since that's on the same energy level, I have to fill that one before I can move up to number 2. And so then I put them in negative. So then I went positive, negative here, and then I go positive, positive, positive. If I was going to go 3p or 2p4, I would go back in and then add the negative. Okay? Yes? No. If it was 2p4, let's say that we're looking at oxygen.
But then that one would be singular occupied, so it doesn't matter.
It would not be singly occupied anymore. Right? This would have a second occupant. This has 2. These are singly occupied, so they have to have the same spin state. Once we add a second, then it completes the orbital. Okay. What other questions do we have? It doesn't seem like it would make a big difference about the order we fill it in, but you really need to get into the good habit of if we're in p orbitals, let's say these are the 3p, and I need 5. It's not a good habit to go 1, 2, 3, 4, 5. Right? That's not technically how they should be filled in. It should be 1, 2, 3, 4, 5. Yes, it looks the same by the end, but you need to get into the habit of filling across and then coming back. Okay? Yes, Charlotte. 2p2. All right, let me just write it out here. 1s, 2s, 2p. You still have to draw every line. That's a good question. So I'm going to fill my 1s orbitals. I'm going to fill my 2s orbitals. And I'm going to go 1, 2. And then I just stop. I have to draw that one, but I can leave it blank. Okay? Because that is an unoccupied orbital. So it would say, if I was looking at the p orbitals, I would have an electron, let's say here, and an electron here. Okay? Yes?
Are the orbitals like actual things, or are they just like...
They are actual electron pockets that they sit in. Mm-hmm. Okay? Let's try boron together, and then you can try a couple on your own. You don't have to write out their whole electron configuration. You can if it helps you. But we know boron ends in 2p1. Right? So I'm going to draw the 1s orbitals, the 2s orbitals, and the 2p orbitals. I don't think we need 3p. Boron is 2p1. So here's how I fill this in. So watch the pattern I use when I fill it in. I'm going to completely fill the 1s orbitals before I move on. Okay, I don't do this. This is not what I should do. I'm not going to go all the way across and then go back, right? That's not how it works either. We're going to fill the 1s orbitals before we move on, so positive, negative. We're going to fill the 2s orbitals, and then how many do we need in 2p? Just one. Okay, do you need to draw these other two lines? Yes. All right, we have to represent all the versions of the p orbitals, and we know that only one is full. Do I need to write 1s2 down here? No. You don't tell me how many electrons are in their orbital, you just show me. Okay? You show me with the arrows. You tell me what type of orbital it is, and then here tells me how many is in that orbital. Okay? Questions about that? Yes, Alice.
So every little space except for the last group of them should be full.
Right.
Okay.
Right. If I go all the way to 4D, everything should be filled before that except for the 4D. Yeah, good question. And there's no way to abbreviate orbital notation, so you do just have to draw it all the way out, even if it's a really long one. Okay, so try those last two on your own, fluorine and neon.